We are now reached regression ERPs, and I want to give you a little bit of my motivation of how I even reached there. And I'm very happy that Olaf is also there because, like, I think without Olaf, I would never sit here in the first place. So I'm generally interested in eye movement in the visual sense, and we do eye movements all the time, right? So this is a video here done with Anna Gerd, and you can see there's a person just in a shopping mall looking around. So this blue dot that you have here is the current gaze fixation. But the person does also many other things. It moves around, right? It makes decisions, etc. So there's a multitude of things happening all at the same time. And I started out with this, how do you even start analyzing something like that? What do you do if people move their eyes, right? You have all bunch of problems that I will discuss in a second. But why is this important to allow people to have natural environment? And I think, yeah, all of these things, if you're interested in any of these, like, I don't know, mobile navigation, VR, gaming, reading, talking, if you do something with infants, something with sports, etc., you all need to break out of this really reduced lab setting, and you need to allow for eye movements, you need to allow for other motion as well. And I really think that Unfold is one step closer to that. I don't think we're reaching there yet at all. There's many limitations as always, but it's probably better than taking means of ERPs. But I'm very excited to see what others people have are coming up with. Any case, eye movements are super important. So if they are also super nice and cool things. So if you here recorded my eye looking at some kind of poster, I could record EG at the same time, and then I can use the stable periods, the fixations, I can use as event markers in my EG, right? And that gives me suddenly I have 4 trials per second, so a huge amount of data. I can cut it. I can do very beautiful plots and contrasts with something like that. Well, the problem, and this is something again back with Olaf. Olaf described this way before I was ready to do something like that. There seem to be like 4 problems that we have to address in order to be able to do eye movement and EEG in the lab now. This is not even in mobile. First of all, you have to integrate the data, so you have to send all this, the triggers around. You also have this muscular artifact, not like the dipole artifact of the eyeball moving and then moving a lot of charges around. And so you get these huge artifacts from blink and from eye movements. So you have to correct for that. But then you also have this, what I mentioned before, this overlap problem, and you have this nonlinear or linear covariate problem as well. And I think these 2 things are pretty much solved. So with lab streaming layers, with triggers, also people know how to, they know how to do that. And for this one here, we have ICA, and especially for eye movements, Olaf has this really cool algorithm, OptiCat, that optimizes ICA for eye movement. So I really think these are done, right? No, not 100% done, but we have a good enough version right now. And these were not, and so this is why back in 2015, I think we met and we came up with Unfold with this regression ERP framework, trying to address this issue. Okay, this is my motivation of how I look at this field. Now let's have a little bit of motivation. I mentioned before that that mean and is just a fancy regression. So let's break that up a little bit. Imagine you have a kind of, I have to close the chat, I'm getting distracted. It was a pupil lab side tracker, just for interest. Imagine you have like this kind of free lab setting where you're allowed to move the eyes, and you can move the eyes on faces or you can move the eyes on bikes. And that's the general example I will give throughout the experiment. And let's say you're interested in something very, very simple, just the P100 for faces versus the P100 of bikes. Does that make a difference, right? Whether this is a sensible question, I postpone, but there's typically some kind of contrast of interest. And now we're gonna find a complicated way to write exactly this thing, right? And this is based on a linear model. So basically, this notation here tells you, okay, let's take the P100 of a phase trial of the of the first phase trial here, and we can write that as a sum of 1 times just the phase beta plus 0 times the difference between bikes and faces. And bear with me, this is might, like if you have never heard about linear models, this might sound a little bit insane, but you will see there's a logic to that, right? So this is the sum of it, plus there will be some error that's specific to that one trial, right? Because you will have other trials, let's say here, a trial of a bike, and now you also take the face beta plus 1 time the difference of the bike minus the face, right? So this together gives you then the activity of the P1. And then you don't only do that for your 2 trials, but you have many trials, many repetitions. And I now notice that I have a car here instead of a bike. Sorry for that. So you have different trials, right? And some of them are faces, some of them are bikes. And now you can take out basically this notation here and put it in this kind of matrix, and we will look at that later in the next section a little bit more detail. And you can put out these parameters that you don't know yet. This is this is kind of giving you the ERP. You put it in here, and now you have a vector here of errors, and this error you just you just try to minimize it as much as you can. I don't want to go much more into the detail here, but in the end, what you want to learn from the data is this. This here, called the design matrix, sets up the structure of your data analysis. Here is a very simple structure. We just have 2 conditions, so we just have 2 columns here as well. Exactly. You can also summarize this a little bit in this matrix notation. I will also show that in a second. And now where are now the means encoded? The means are encoded in this beta here. This is this mean here, right? So this beta here is the mean. And this beta here you get by adding these 2 parameters together. And that's the complicated way to write your mean. And that is one way how the mean and the linear regression is related. And this will give you exactly the same results. That's my promise. But now why bother? Why making this so complicated, right? It's a very good question. And sometimes it's just not needed because the results will be completely identical. But you could have here, especially if you do an eye tracking experiment, you could have, for instance, have some continuous confounds. So maybe you like bikes more than people, and then you do larger eye movements on bikes than on faces. And if now an eye movement also makes a certain response in the brain, then you might get just a confound simply because people do larger eye movements. Or there could be also an effect that Olaf described. There could be an effect of stimulus position, because if you look at the left side of the stimulus, then suddenly you have much more background here. Then if on the right side you have much more background here. So you could expect some kind of lateralized activity as well. Okay. What you take away from this is mean and regression is similar, and regressions are awesome, and they have this kind of different things, like the design matrix, and they have the parameters. And we will now we will now introduce time into this whole dimension, because typically you don't only interested in the P1, but if you could think of calculating an ERP, you get a curve over time, right? So you don't only have one time point here, but you have many time points for each of these trials. So these are our single trials. Also, typically, you don't want to build this design matrix by hand, but you use what we call the Wilkinson formula, and I will have a little bit more detail about that later. But basically, it just means this is the left side, this is your trials, and these are proportional to your right side, and this describes your design. The 1 is always the intercept. It's a little bit complicated. I will not go into details here, but now you heard it. This is the intercept, also sometimes called constant. Okay, so we have this data here. Let's pick one of these, like we had on the previous slide. We're just going to do the same thing that we had on the previous slide, so nothing new per se, except that we have more time points here. We're also going to build this design matrix, so you're kind of familiar with this now. You have the intercept and you have the difference of the one condition to the other one. You have the parameters here, you have the error here. And now we already fitted basically this one parameter, and we get one value for your beta. And now what we simply do is we repeat this for each time point. We shift it over, and at the same time, we get this ERP curves. And now, because of the special coding that we are using here in the design matrix, and that coding is important, but I don't have too much time to talk about this, because we have the special coding here, this first column is an actual ERP you would get for the face. And this one here, because it just is the difference, it just has a 1 whenever there's a difference of when there's a bike. this is actually like a difference curve, like a difference between two ERPs, basically. What you should also be familiar. So both of these things are already familiar, and yeah, I hope that yeah, you can kind of appreciate that. So now I did discuss this Wilkinson formula a little bit. Let's have a look a little bit in more detail, because yeah, oh, this should be to the one. Sorry for that. If we think of this left side, it's not so important for us. But if you think of the right side, that's more important. And what's a little bit hidden here is we are writing here some name, and this name will later be looked up in an events table you will see in the exercises and understand that better. So you have some kind of table, like an Excel table. You can think like a sheet. Where you have on top, you have for each of the trials, you have, let's say, a stimulation, whether you stimulate it with a bike or with a face, and the size, maybe the size of the stimulus can be changed, large and small, etc. And for each trial, you have an entry, what the actual level is it. Maybe this is big, middle, small, and maybe this is bike and face. And so now the Wilkinson formula looks at this formula, what you want to model, and it looks at the event table, what type of variable is there, and then it actively directly takes this information and generates the design matrix for you. So there's nothing more you need to specify than providing the events table you have and this kind of formula. And if you then later want to have a different model that doesn't take size into account, or maybe even takes the interaction between these two things into account, then you can simply modify this formula, and that's quite nice, I think.
Bina, we have a question in the chat about the intercept, whether we always keep it equal to 1 or whether there are other designs that require other numbers for the intercept.
Okay, yeah, it's a good question. The intercept is really special, and it is always 1. There's no, like, I'm not aware of any. What you can do is you cannot use the intercept. So in this matrix here, what you could do is you could have a column that has 1 only when the faces are, and a 0 when the bikes are. So like the different the how do you say, the complements to this column here, and then you would get 2 ERPs, 1 for the bike and 1 for the face, and no difference curves. But as soon as you add more effects here, like not only is bike but many other effects, then an intercept is typically something that you would want to have. This column here, and we will see that also in the second part, this does not typically does not need to be zeros and ones. This, if you have zeros and ones, it's called dummy coding, but there's also a way you can have effect coding where this would be minus ones and ones, and it has certain benefits in interpretation. But yeah, I'm skipping this for now, even though it's an important comment. I do have it somewhere on the slides later. Yeah. Thanks for the question. It's helpful. Okay. A little bit of history of all these kind of things before we go to how you actually do that in Unfold.jl, and how you yeah. For another talk, I put together this I tried to find out what is the rules of these different thoughts that we have here for regression, ERP, etc. When were people first doing this? And this is just, I think, to highlight that this is Unfold. Sometimes people say, oh yeah, I unfolded this or something like that. But this is like really, many people have been using these kind of tools before. We are, of course, very happy if you do that, because, well, it sounds also cool to you can unfold your potentials, right? This is our tagline. But yeah, please be aware there are many other people who have done it before, and we are standing on the shoulders of giants. We basically just put it together in an easy to use. Okay. And also be aware there are many reinventions, and so different, like, these things are pretty much all very, very related and similar, but they can have extremely different terminology because they come from very different views of the world. I'll put that up here. You can look it up later, but this is more for reference. I don't want to say more about this here. Now let's have a look of how we are going to implement such a model that we had that we just did. How hard or easy is it to do that in Unfold? And first of all, you're going to start with some kind of data. And if you're an EG Lab user, then this kind of array should be very familiar for you, because it has the same EG Lab kind of structure. You have channels, you have time points, and then you have epochs, right? If you have only 2 dimensions, then typically we have only 1 channel. And this is also the same. For most of the exercise, we will only work with 1 channel. But there's also like an advanced question where you could play around trying to get this to work with multiple channels as well. So this is our data. This is just a straight out floating numbers array. And what we also need is an events. This is a data frame. So this is like a table that you have that you will also immediately see in the exercise. It will contain, I was discussing this before, it will contain the information about each of these epochs. What kind of epoch is it? Is it a large, is it a bike, etc. Finally, the last ingredient you need to define the model that you actually want to fit. So in this case here, we are using this funny syntax. It's called add formula. And the add, for people who know a little bit more about programming, is like a macro. So it's like a meta programming tool. But for most people, we don't care. Just this is the syntax. You also need to write a 0 because we are providing the data extra. It's not in the data frame, so we don't want to confuse the computer. And then here you write whatever linear model you have thought up. Then you put it into a fit command. You tell it, I want an unfold model. Don't fit me a linear regression or something like that. Unfold model, that's what we have. Formula, event table, data, and then we have a times vector, which is just a kind of like a convenience. So the output is a little bit nicer, so we know when in time you are. And that's just a vector, like eg.times in some sense. Right, once you have that, you can get the coefficients in a matrix format like this, or as a table format like this, and there are many other tools. But you will also, you don't need to remember any of this, because in the exercise we prepared it for you, and you should be able to do it. Okay, how do you get to the exercise? So now what you need to do is something that I hope you already done before with the installation notebook. You need to go to our website. You need to go to materials. Then you need to copy this first notebook to your clipboard. You need to have Pluto open and put it in this open a notebook file. You need to say, yes, I understand. This is from outside my computer, blah, blah, blah. And then in the top, you need to run the notebook code. This will take like, between 5 and let's say 40 seconds, depending on how fast your computer is to start up. And then you can actually independently on your own run through the workshop material, the first exercise. For this first exercise, you have until 11:30 plus then 15 minutes of break. That's kind of our deal. So you do have some time to do it. Please, Romy will put up the slide of how to ask questions, and then, well, we're going to answer them one-to-one or in GitHub, etc. So make use of this. We are here the whole day just to answer questions, basically. Yeah. Okay, cool. I hope that was a good chunk of information, and that you then have fun and enjoy the exercise.